What is finite element analysis? FEA is a method engineers use to predict how a part reacts to real-world forces such as stress, heat, vibration, and fluid flow before it's manufactured. In FEA, we turn a part into small shapes called finite elements. These elements are connected at points called nodes. This entire system is called a mesh. During simulation, we add constraints and forces, and the software uses linear algebra to calculate stress levels within the mesh. This video will cover how to set up an assembly, tetrahedral meshing, and a von Mises stress simulation. Stress simulation is important so we can design parts that don't break easily. For example, we might want to know how much force I can exert on this handle before fatigue failure. Let's model this. Today, we are going to learn how to do finite element analysis on Siemens NX using the 3D mesh technique. We're first going to open an assembly. It's pretty simple. We have two bolts holding two plates together. Let's say we want to do an analysis where this end is held fixed and this is being pulled on this other end. And we want to see the stress distribution within the assembly. First thing first, click on Application. Click Pre-Post. Pre-Post is a feature that creates two new files, a FEM file and a .sim file. The FEM file contains the assembly meshes and the sim file contains the load distributions, constraints, and the actual simulation we're looking for. Now, let's press on Pre-Post. Okay, license error. Okay, go to the command finder and look up licenses and manually add in all the licenses. After pressing Pre-Post, you should see something like this. Click on New FEM and Simulation. Make sure to create idealized part as checked. All visible bodies, standard resolution, structural, and none for 2D solid. Click Create Solution. Default settings are fine. Click OK. To set the center of rotation, click View, Fits, and press Ctrl F2. Let's start by clicking on Mesh Collector. A mesh collector allows us to define different material and mesh types. Make sure it's on 3D for element family and solid for collector type. For material selection, click on Create Physical and then choose Material. Here we have a list of built-in materials. Let's do 6061 aluminum. Make sure element type is on structural. Click OK. In our case, we have multiple materials. Our plates are aluminum and our bolts are steel. This means we'll need to make a mesh collector for each material. Click Mesh Collector and repeat the same process, but we're going to use IC 310 stainless steel. Now we have two mesh collectors. We can actually view them by going to this drop-down menu. Under 3D collectors, here are meshes. Click on 3D tetrahedral. Select our aluminum parts under Objects to Mesh. Select Solid 1 for the mesh collector. Let's talk about element size. The smaller the element size is, the higher the accuracy, but it would require longer compute times. If the element size is set too big, it's easy to miss small stress concentrators. On parts with small tolerances, however, I start with a finer element size. But for larger parts with larger surfaces, I start with a larger element size. What I usually do is I start with a medium element size and iterate lower to see what stress levels converge to. In our case, let's make the element size 3 millimeters. Click OK, and it will generate a mesh for selected parts. These are 3D tetrahedral shaped elements. Now, we will do the same thing for these two steel bolts since they are different material. Select the two bolts, use 3 millimeters for element size, and select Solid 2 for mesh collector. All of the objects now have individual meshes, but the problem is the meshes aren't connected to each other. Click on Mesh Mating. There are 3 different mesh mating types. Glue coincident mates 2 touching surfaces together. Glue non-coincident allows 2 surfaces that aren't touching, but might touch when under load, like distance mates. Free coincident allows objects that aren't touching at all. Let's say we want to bind the top of the plate to the bottom of the bolt head. Select the plate as the source face. Click on Body Focus and the bolts to isolate it. Select the bolt head bottom as the target face. Click Glue Coincident and OK. Click Update to see if the meshes connect. Repeat this step for the other bolt head. We still have to bind this surface to this one. When mesh mating, make sure it's on manual creation because auto creation sometimes doesn't work. We use the same process for the interior of the plates and the bolts. We do this for both plates. Last one. Interior of this plates and this bolt. And we finished our assembly meshes. Make sure to update the mesh. Click Activate Simulation. There are many different load types to choose from. For constraint types, I use user-defined constraints so I can manually select degrees of freedom. For example, if we want this wall to be held in place, like a cantilever, we can say all the degrees of freedom are fixed. These degrees of freedom represent the x, y, and z displacements and the x, y, and z axis. Let's say there's a static force pulling the object at this end. We select the surface under model objects and set the force magnitude. Let's say 1,000 newtons. And we specify the direction to be along this vector, this way, for example. Then, for method, use geometric distribution so the force will be spread out along the surface. Click OK, and forces are pulling this way. Click Solve, press OK, and this window will tell us if there's an error we need to fix. Alright, no errors. Simulation is done. Feel free to close the windows. Under this results folder, right-click Structural, click Open. Here's a solution and it gives us different visualization options. Let's click on Stress. Now we can see where the stress buildups are. The false color bar on the left shows approximate stress in megapascals. It looks okay, right? It's actually not. It's red on the bottom here. Let's say we want to see a cross-sectional view. Click Cutting Plane Options. We can choose the X coordinate to cut through, or we could cut by node, like this. Let's say we want to cut here. Press OK. And there we go. We just did finite element analysis using the 3D meshing method. If you want to use a 2D meshing technique to get shorter compute times, check out the video in the description below.